Students, in this video we'll prove that the roots of orthogonal polynomials interlace. So if we're given a sequence of orthogonal polynomials, phi 0, phi 1, phi n on AB with respect to the weight W, then phi n vanishes once, exactly once, because they're simple roots, between consecutive roots of phi n plus 1. Okay, and so this is called the interlacing theorem, right? This is the interlacing, this is the orthogonal polynomial interlacing theorem. Okay, and of course, let's recall some basic facts. Recall the roots of phi n are all simple, real, and real. Okay, excellent. And so what we can do is we can say phi, therefore the roots of phi n are going to be alpha 1 through alpha n, for example, right? So let's suppose, and one more thing too over here. So recall this, so for the previous video, and also phi n plus 1 minus sigma phi n also has, and that's a polynomial degree n, so of course this thing over here is perpendicular, is orthogonal to phi n minus 1, phi n minus 1, phi n minus 2, phi n minus 2, all the way down to phi 0. So this thing has n plus 1, simple real roots as well for any sigma. We can just run the same argument, right? Because the whole point is that what we can do, so for we'll call how the proof of that went. The proof of that went as follows. So the proof of that fact went like this. The integral from a to b of phi n plus 1 minus sigma phi n, and then times x minus, those are x's of course, x and x minus, let's say alpha 1 to x minus alpha L, w of x dx. Where these alpha 1s were the what? Were the roots of odd multiplicity, right? So if those things had odd multiplicity, then of this function over here, then this thing would have even multiplicity when you multiply it out. And so I know that this will be perpendicular if L was less than, say, for example, n minus 1, because that's the only way you can have enough of those odd simple roots, then that would be perpendicular to this thing, so this would be equal to 0. But now, once you pull out all the odd multiplicities over here, you can conclude that this thing is also greater than 0 because it's going to have the even parities and everything with respect to a positive weight, right? So that's a contradiction, right? So in other words, this thing for any sigma phi n plus 1 minus sigma phi n also has n plus 1 simple real roots for any sigma, right? That's going to help us with our interlacing theorem, right? And so now let's suppose, so here's the proof of interlacing, Okay, let's suppose that phi n plus 1 has roots, has consecutive roots, lambda 1 and lambda 2. Lambda 1 and lambda 2. Okay. And phi n plus 1, or just phi n of x, is not equal 0 for x between lambda 1 and lambda 2, right? For lambda 1 less than x less than lambda 2. Okay, and also equal to, right? Because I know that they can't share, I know that phi n plus 1 and phi n cannot have common roots, right? So in other words, it's not equal to 0. Then construct a new function, construct h of x, which is going to be phi n plus 1 phi n plus 1 over phi n of x, right? Then h, of course, is a perfectly well-defined function on the interval for those values of x on that interval over there. So h is well-defined since phi n is not equal to 0 between those consecutive roots. And now I know that h of lambda 1 and h of lambda 2 is 0. H of lambda 2 is equal to h of lambda 1 is equal to 0. So by the mean value theorem, h prime of zeta is equal to 0 for some zeta in the open interval lambda 1 to lambda 2, okay? Which tells me what? Which tells me that phi n of zeta, phi n prime plus 1 prime of zeta is equal to what? Is equal to, it's the bottom times the root of the top minus the top times the root of the bottom. Phi n prime of zeta, like that, okay? In other words, the ratio of phi n plus 1 and phi n at zeta and phi n plus 1 prime and phi n of zeta is the same, right? And so now the final step is to do this. So now let's look at g. Let's look at g of x, which is going to be equal to what? Which is going to be phi n plus 1 of x, and then minus this ratio over here, minus phi n plus 1 of zeta over phi n of zeta, phi n plus 1, phi n of x. Now if I plug in, now g is a what? G is of this form over here. G is the form phi n plus 1 plus a minus a number times phi n. So it's this form. So I know that this g has what? Has only simple roots over here, right? But what do we know about g of zeta, for example? G of zeta is equal to 0. Right? Because if I plug in zeta, that's going to cancel out. And g prime of zeta is going to be what? Well, g prime of zeta is going to be what? G prime of zeta is going to be a prime over here, a prime over here, a prime over here. When I plug in zeta, I know that I can replace these things over here. I can plug in, I can put prime here, because those ratios are the same. Prime, prime, prime. And so what is g prime of zeta? G prime of zeta is going to be equal to 0 as well, and that's a contradiction, right? So in other words, because I know that g only has what? G only has simple roots, so my assumption that my polynomial over here, phi n, did not vanish between lambda 1 and lambda 2 was wrong. Therefore, between two consecutive roots of phi n plus 1, there must be exactly one root of phi n, and now we've shown that that's what I call like an interlacing. So if I plot all the roots of phi n plus 1, in between all those roots, I can fill in the root of phi n. In between all the roots of phi n, I can plug in the roots of phi n minus 1, and so on and so on and so on and so on. Look at this interlacing this weave of the roots of these orthogonal polynomials, which comes up a lot in the study of Jacobi matrices, in the study of linear algebra for spectral problems for these sort of tridiagonal matrices, which we'll discuss in further videos. Thank you very much.